There's something very unique about angular displacement. Let's look at this picture over here. We already showed you earlier how, let's just look at the outside. There was a bug here at point A. Now we're going to call it point A sub 3. Moved over to B3, or the object rotated that way. You know, either the bug's crawling there or the whole object's rotating. We covered an arc length. In this case, we're going to call it S3. And it's subtended an angle of theta. So here's one circle, this guy right here. Now let's take this next circle, this little circle here, the inner circle, circle 2. All right, we have again another point A2. A bug moves from A2 over to B2, covers a displacement of S2, and then the same angle theta. We will then move on this last circle with a radius of R1, arc length of 1. You move from point A1 to B1. You go along this arc length and you still cover the same angle theta. All points on a rotating rigid disk move through the same angle theta, but they have different radii. Can you see how this first circle had R1, then R2 was a little bigger, R3 was the biggest, and they each had different arc lengths, but one thing was the same. The angle theta was true for all three of these concentric circles. Since theta is constant for every point, right? I could have taken any concentric circle here. I could have put somebody over here and had them rotate around. Somebody here could have rotated around. Theta is constant for every point as I rotate. It describes something very fundamental about this rotating disk. That's why it's been given this very special name, angular displacement. We can now relate angular motion to linear motion. We've got the definition we need. Linear motion has already been covered in the kinematics section of this course. We have now defined the radian. Angular displacement is defined. Of course, angular displacement is this quantity right here, theta, which tells you how far the circle has rotated, and radian is the unit that we use to describe angular displacement. Much like for regular displacement or translational displacement that we've already gone over in kinematics, the meter was the measurement. Now we're using the radian to measure angular displacement. The object at point A1, let's take A1 in here, rotates to point B1. It covers a linear displacement of S1, which is going to be measured in meters, and an angular displacement of theta, which will be measured in radians. Same thing for points A2 and A3, but as you can see, even though theta is the same, the arc length increases the further away you get from the center of the axis of rotation or the circle. Using our definition of the radian for these 3 points here, A1, A2, and A3, as they rotate into B1, B2, and B3, we show how the linear displacement, which is S, increases directly as the distance of the point from the axis of rotation, the radius of whatever circle it's on. The angular displacement, theta, remains the same for a constant rotation for all points on the disk. Here's our definition of radian. Theta is S over R, or angular displacement, of course, that is measured in radians. Just do a teeny bit of algebra, and we find that the arc length is R times theta. So we just do it for each individual point here. S1 is R1 theta, all the way to S3 equals R3 theta. So since theta is constant for any rotation, the further you are out from the center, the greater your linear displacement.